Good morning, everyone. I want to welcome you to another Motivate statistics class. Of course, the focus today will be on bivariate normal distribution. Before now, I introduce you to normal distribution. Of course, I remember on Monday, I actually highlighted the significance of normal distribution in statistical world and research world in general. And of course, I remember the focus on Monday was actually univariate. Univariate in the sense that the focus is on, we're focusing on one measurement at a time, which could be blood pressure, it could be stock return, it could be GDP and so on, like that. And of course, I remember I gave you the functional form of the distribution, and I also walk you through the essence of standardization. Okay, reason why we need to standardize normal distribution. I think I mentioned something that I call for simplicity of probabilistic computation, and I also gave some probability calculations. And from there, we're talking about affine transformation. Affine transformation where there's possibility of a linear relationship, or a linear combination between two variables in such a way the first variable follow a normal distribution, and of course automatically uh, you know, the other variable will also follow normal distribution. And I think I finished that with parameter estimation. Okay, so if I actually investigate, maybe graphically, the distribution of my data set, maybe using the histogram or stem and leaf plot or box plot or density plot, and you find out that the data set follow normal distribution. Now the question now is, how do we estimate parameters, okay, of a normal distribution? I think I also walk you through that. I remember we use a method of maximum likelihood, and I also show you how to do that now. But what of in a situation where the focus is not just on one measurement, but the focus is on two measurements? I'm actually going to pretend to be a physician, a doctor, a medical doctor, or who is focusing on the height and the weight of the patient, height and weight. So those are two, it means I'm actually want to consider two measurements at a time. And of course, using univariate, idea of a univariate is not going to work because I got two measurement at a time. So when I have two measurement at a time, we actually, and each follow normal distribution, or they jointly follow normal distribution, and that's going to be the focus today. So today, we're going to be focusing on bivariate normal, so which means in the outline, okay, this is what we actually going to deal with today. I'm going to give you the distributional form, the probability calculation, the affine transformation, and conditional distributions. Now, let me prepare your mind. Let me prepare your mind. This is going to be mathematical intensive, but don't be scared. Just pay attention. Okay, just pay attention. Okay. Now, I want to go into that right now, the bivariate normal. Okay. Now, but before going into this bivariate normal, do you know that somebody can argue this out? Why am I interested in bivariate normal? If blood pressure, if let's say height of my patient follow normal distribution, and the weight of my patient follow normal distribution. Okay, so why can't we just translate univariate into bivariate? I'm going to say that again. If the height, if I'm considering height and weight of my patient, and height follow normal distribution, weight follow normal distribution, then does the marginal distribution translate into joint distribution? And my response is no. The fact that each of the variable follow normal distribution does not necessarily implies that the joint distribution will be normal. And the reason why that does not translate into that is because, if I consider them separately, then I'm actually ignoring relationship between them. I'm going to say that again. If I consider, if I consider the variables separately, then I'm ignoring the potential relationship between them. Okay, and situation where the potential relationship between them induces skewness. If it induces skewness, if it's actually not going to be double bell anymore, the joint is not going to be a double bell shape anymore, but it's going to be elliptical in nature. And that is the reason why univariate normal distribution does not necessarily translate to bivariate normal distribution. And that is the reason why I need you to pay attention now. Oh my God, if you look at equation 5, I'm actually having, this is called a bivariate normal density. I have f of x and y. Okay, if you take a look at what I'm seeing here, this is more or less an extension. This is an extended form of what I display on Monday. Okay, what I display, the density that I display on Monday only focus on the mean of S and the variance of S. But right now we are having it combined. And if we take a look at the function here is no longer f of s, no longer f of y, but f of s comma y, because we got two variables. Now, do you know that in this now, you're actually gonna have, the mean of x, there's gonna be mean of x, there's gonna be mean of y, there's also gonna be variance of s, you're also gonna have variance of y, and if the variance of s and the variance of y exists, then we're also gonna have the standard deviation for x and y. And not only that, we're also gonna have I need you to take a look at this guy. That's a row correlation. Okay, a row is a correlation, which means in this bivariate architecture, okay, we actually incorporated what could measure the relationship between the two variables. But there's something I really want you to pay attention to here. Imagine we plug in 0 for row. If I plug in 0 for this guy, and I plug in 0 for row, and I plug in 0 for wherever I see row, that means relationship does not exist between x and y. What I'm actually going to get will be a product of what? It's actually going to be a product of the marginal density for x and for y. And that is the reason why in statistical analysis, give me 1 second. Now I need you to pay attention to that. If rho equal to 0, which is the correlation between x and y, if it is 0, then x and y, they will be independent. So if x and y are independent, the joint f of xy will be equal to the product of the marginal density. Okay, which actually means x and y are unrelated. Okay, so what actually measure relationship, the parameter that measure relationship here is actually the rho, the correlation. Does that make sense? Okay, so and and that particular rho, okay, actually going to be less or equal to 0. It's going to be less than 1. Okay, why do we say less than 1? Is because if relationship exists between two variables, it is not necessarily a perfect one. Does that make sense? So this is a bivariate normal density. And of course, uh, bivariate joint behavior could become marginal if you plug in 0 for all, which means there's no relationship. That's what that means. Okay, is there any question on this particular architecture before moving forward? I really want to know if there's any question. So if X follow normal distribution and Y follow normal distribution, okay, then that does not translate them into having a joint normal density. So, which means we need a test, okay, a special test to conduct, on the bivariate, whether they are jointly normally distributed. Even though you have already seen that distribution of S is normal, distribution of Y is normal, but you still need to conduct a test to be able to investigate whether they actually going to be distributed jointly, normally jointly. Does that make sense? Now, I want to go into um, you know, pictorially, we actually want to have a way to represent bivariate density. We want to go by way of by graphical way, to actually represent density, the bivariate density. Now, I told you the other time, the parameters we got a lot of parameter in the bivariate density. Okay, we have a mean of x, we have a variance of x, we have the mean of y, the variance of y, and we also have a correlation. Now, it means if I actually want to pictorially represent, then that will depends on the that depends on the variances and the correlation between the two variables. Okay, so that depends on the variances and the relationship between the two variables. Now, right now, if you take a look at what I'm displaying here, what if in a situation where the mean of the two variables are equal and it is 0, and they have different variances, okay, and this is a correlation between them. Let me tell you this. What is going to determine the shape, okay, of this particular plot that I want to show is difference in variances and the correlation between them. Okay, now I'm actually going to start from the surface plot. This guy, please pay attention. I want to explain that. Okay, the surface plot. The surface plots that I'm actually having now, give a surface or representation, okay, of the bivariate density in 3 dimension. 3 dimension. Okay. I just wanted to look at that. When I say 3 dimension, you can see x, y, and the f of xy. Can you see that? Let me show you here. This is f of xy, this is x, and this is y. That's why it is three-dimensional. The surface plot is 3D dimension, 3D survey plot. Now, uh, if you take a look at the peak actually going to be centered. I want to award an extra credit now. I want to award an extra credit. Can somebody tell me what is, I want us to read this point. It is centered at two coordinates, this here. What is that point? Can somebody tell me? Go ahead. Is that one? Okay. You mean at the two means, right? And what did they give us as the value for the two means? Good job. Send me a message for extra credit. So that is centered at 0, 0, centered at the mean. Don't forget, the center of a normal distribution is the mean, which may represent the peakiness, the height of the curve. Okay, now let me tell you the maximum probability, occur at that particular point. That's what we mean. Does that make sense? The highest probability actually occur at that particular point. And let me also tell you this, looking at the shape, I'm still focusing on this 3D plot, surface plot. This very shape can actually be determined by variances and correlation. The variance of x, the variance of y, and the correlation between them. Does that make sense? That makes sense, right? Now I want to move to another plot. Okay, this plot. Now, if you take a look at that very plot, this plot is a two-dimensional. Okay, and of course, we actually using a color gradient here. We call this heat map. Heat map. Now, let me tell you this, the warmer color, when I say warmer color, I mean red and yellow. Okay, red and yellow indicate the density region with high probability. I'm going to say that again. The red and yellow, that is the warmer color, actually indicate the region with high density, high probability density. Now, when you look at the cooler region is blue and purple. That's so cool. Talking about cool in terms of color, okay? And of course, that actually represents the region with the lower probability, the lower density, probability with the lower density. So I just wanted to take note of that. And of course, we have elliptical shape, okay? And that very elliptical shape align with the correlation structure. That align with the correlation structure. Okay. Now that's what we mean. That's heat map. It's actually this is a color gradient. Okay, I want to go to the next one. Okay, I needed to pay attention. Okay, when you take a look at the one I have now, it's what we call contour and marginal, distribution plots. Contour and marginal distribution plots. And of course, I'm actually going to explain. Let me start with the black scatter plot. Okay, you can see the black scatter plot, all those ones. Okay, they actually represent the data point. Okay, from the bivariate distribution. Okay, they represent sample from bivariate normal density. Okay, you can see the X, you can see the Y. That is what that means. Okay, now we want to talk about the green. You can see this guy. You see that green color, right? That's exactly what I want to explain all right now. Now, the green ellipse shows contours of equal probability. contours of equal probability. That's what the green show, contours of equal probability. I'm going to say that again. So the green ellipse shows the contours of equal probability. Contours of equal probability. Now let's focus. This I can see a red histogram here. I can see the blue histogram here. Of course, each histogram represents the marginal distribution of the respective variable. Don't forget here we are considering two variables, right? There's going to be a marginal density for one variable, the marginal density for the other variable. It will give us, an avenue to see whether on their own, what kind of distribution they each follow. Does that make sense? Okay. So that is all of that. Okay. Now, I think I just gave interpretation of three different plots that can actually be used. Okay, if you want to have a comprehensive understanding of bivariate density distribution, okay, these three plots give us that visualization. Okay, now what I'm just doing here is, what if I have different means and every other parameter stay the same? I got different means here. When the two means are equal to 0, how is the 2D density plot going to look like? When the mean is the mean of the x is 1, the mean is 2, how is it going to look like? Then when each mean is -1, -1, but in each of these plots, I'm actually using, I fix this. Okay, the variance equal to 1, variance of x equal to 1, variance of y equal to 2, correlation. So what I mean, I fix these particular values. The only thing I'm changing is changing the means. So I actually want to see how that shape is going to look like. Is there any question? Is there anyone here who's not really enjoying this, who doesn't really understand what we're doing? Please ask question. If you don't understand what we're doing, ask question. I've been posting my recordings on YouTube. Okay, Zoom link could expire, but what I put on YouTube is not going to expire. So you put my name on YouTube, and for you to be able to, because I put a lot of recordings on YouTube, the one that include this class and the other classes, but make sure you choose your class. I post star 4052. Sorry, star 5401. Then you look at the title. Okay, now this is testing different means. Now, what if everything remained the same and I'm only testing different correlation? Where the correlation is this. That's what I have. The correlation is negative. Are you surprised? Look at the direction. When the correlation is 0, that's what I have. When the correlation is positive, that's what I have. Does that make sense? I needed to take a look at that. And we're changing correlation, but this stay the same. The mean, the variance all stay the same. Okay, we just wanted to see the impact of correlation value on the 2D plots, the density plots. Okay, now this is another one. This is different variances now. Okay, this is different variances. At times we could vary just the variance of y of one of the variable. You see that? Y, the variance of x, and means and the correlation stay the same. Okay, so all we're doing here is trying to looking at the impact. Don't forget, this is an heat map. Okay, we use this color gradient here. Okay, if you want to talk about measure correlation between variables, red and yellow, the warmer color, blue and purple, the cooler color. Okay, now away from graphical structure, I want to go into mathematical framework of bivariate normal distribution. And we actually want to do a little bit of calculus here. And I needed to pay attention. Now, because two variables are involved, I may want to figure out what is the percentage of my patient that we have a blood pressure between A and B. What is the percentage of my patient that we have their height between A and B? If I want to figure out the percentage of my patient that we have the values of their random variable, to be, to lie between A and B, I'm actually seeking a joint antiderivative. Because the normal distribution is continuous, because of that, if I'm seeking to figure out the probability of a random variable, a continuous random variable, of course, I should be ready to perform an antiderivative. But this time around, because I got two variables, then I'm actually going to have two integrals. If I have three variables, that would be triple integrals. The numbers of integrals I'm actually going to have depends on the number of variables under investigation. Now, equation 6 will tell us how we can simultaneously figure out the probability of x lying between two constants and the probability of y lying between two constants. That is synonymous, to a physician, a medical doctor that really want to figure out, have a sense of the percentage of his patient, okay, or that we have between maybe a particular value and a value for blood pressure, and that we have between a particular value and a value for their weight. Does that make sense? Okay, now, if we are doing that, we actually also going to have a cumulative density. Okay, just like the way we have a cumulative density on Monday when we're focusing on univariate. Okay, the cumulative density actually going to accumulate from a lower point to a point X. Okay, from a lower point to point S. That's why you see, well, I want to figure out how the probability of S less or equal to S and Y less or equal to Y. And if I want to do that, I want to perform an antiderivative. I'm actually going to come from the lowest value of X, okay, to a particular point in S, and from the lowest values of Y to a particular point in Y. When I'm doing that, I actually want to figure out the CDF. Okay, now I'm also going to show you, okay, the bivariate normal PDF that I've showed you before, and that's of the CDF. Okay, the CDF cumulates, the PDF give individual, okay, individual points. Okay, of course, I just wanted to take a look at the two. The two are in two dimensions. Now, do you know what I need from you now? Some of you may be wondering. Last week, we were focusing on matrices. Now you're actually going to start seeing the significance of matrices now in the bivariate setting. I need you to pay attention. Now, I'm actually considering two variables. Oh, a medical doctor is trying to consider height and weight of the patient. Height and weight. Maybe X represent is variable height of the patient, and Y represent the variable weight of the patient. And he has conducted a test, and he realized after conducting the test that the joint variable now follow normal distribution. Not just individual variable, joint variable follow normal distribution. Now, if the joint variable follow normal distribution, then the mu here is actually going to be a vector that will contain the mean of x and the mean of y. The variance here is going to be a covariance structure, and that very covariance structure is what I want you to see right now. Oh my God. If you take a look at that, it's going to be 2 by 2. Why 2 by 2? Because two variables are involved. When three variables are involved, it's going to be 3 by 3. When four variables are involved, it's going to be 4 by 4. More than two variables is what is going to be our focus on Friday, where we're going to be focusing on multivariate normal. But right now, okay, the dimension of the covariance matrix is actually going to be 2 by 2. And let me tell you this, in the diagonal will be the variances. The diagonal of the covariance structure of the covariance matrix is actually going to give you the variance of each variable. Okay, sigma square S, now the variance of height, maybe the variance of height, and sigma square Y, the variance of weight. But in the off diagonal is the covariance. This is the covariance, and that is going to be equal to that. Okay, they're going to be equal. That is the covariance. The covariance is a product of the correlation and the product of the respective standard deviation of the variable. I want to take note of that. Okay, now you understand that now? If I have a matrix A, okay, and B, I have a matrix A and B. Matrix A is 2 by 2. Matrix B is more or less like a column vector. Okay, in such a way that the entries is not this. Because imagine you have a covariance matrix that look like that. What are you telling the world? Even though the mean, even though the, in fact, it's not gonna happen. This is not gonna happen. We can never have that situation in the realistic world where the variance equal to 0. Variation within me, okay, if I'm looking at the variation within me, it must exist. It can't be 0. Okay, even though the variation between can be 0, there's possibility. Covariance can be 0. If if the covariance between two variables is 0, that's implied they are unrelated. Of course, we can have that in real life. But what we are not necessarily going to have in real life is when the variance of H equal to 0. That's not going to happen. Now, and I want to consider this. Please pay attention. I have a matrix A and I have a matrix B. Okay, and maybe A follow normal distribution, B follow normal distribution, and I need A and B. If you take a look at what I have, okay, take a look at this. This is X, I mean this is Z, and maybe this particular Z is even this guy. Okay, I need you to take a look at that. Now, but A is a constant, B is a constant. Okay, now let me explain this so that you can really understand what I'm talking about. Let me refer to this as a constant matrix. Let me also refer to this as a constant matrix. Now, the only variable here, please pay attention. The only variable here is Z and W. If Z is a variable, okay, W is also going to be a variable because W depends on Z. Does that make sense? Now, and in this one now, if Z follow normal distribution, we've already said that here. If Z follow normal distribution, then W is also going to follow normal distribution because W depends on Z. Now, when Z follow normal distribution, This is the mean. This is the covariance structure. Then they're also going to, so based on what you have here, they can ask you to determine what will be the mean of W and what will be the variance of W. Now, I'm trying to tell you right now, please pay attention. The mean of AZ is going to be A mu, because A is a constant. A is a constant. So I'm trying to say the mu here represents the mean of Z. Does that make sense? But what is the mean of Z? The mean of Z, don't forget, is this guy. The mu S comma mu Y. Now I also want to seek for the covariance now of W. I want to get the covariance of W. Please pay attention. To get the covariance of W. Now, like I said, the mean of this one is this guy. You have to add a constant because expectation of a constant is a constant. But I'm seeking the variance of W now. Now, in the variance of W, B is a constant. Expectation of the variance of a constant is 0. That is not going to be part. I'm only going to be focusing on AZ. Okay? And that is going to be this guy. I'm going to have A variance covariance A transpose. Does that make sense? Okay. Pay attention. A lot of exam questions here. Now, I want to go into conditional normal. And I need you to pay attention. Conditional normal. We actually want to benefit from relationship between two variables. If relationship exists between two variables, if I have information about a particular variable, can I say something about the other variable? That is conditional. That's what conditional means. Now, take a look at this. From mathematical formula, the conditional distribution of y given s is actually going to be the ratio of the joint to the marginal of x. You've done this in lower level statistics. Okay? So the f of xy is the joint and the f of s is the marginal. Does that make sense? Now, we actually we can start by, please pay attention. This is very useful in research world. If I put the bivariate density here, you know the bivariate density? I'm going to show you now. Yeah, this guy. If I put the whole of that is the joint f of xy, right? If I put it in a numerator, here, the f of s, I only put the density, the marginal density for normal in the denominator. And what I want to derive is a conditional distribution for y given s. That's exactly what we're doing here. Please pay attention. That's what we're doing here. You see that? In the numerator, what do you see? The bivariate joint. In the denominator, you see what we have? In the denominator, we have the marginal. Then when we derive it, please pay attention. This is what we have. We got this guy. Now, based on what we have, based on this, okay, we need conditional mean, we need conditional variances. I'm going to say that again. We need conditional mean. We can only get conditional mean and conditional variances from conditional density. This is a conditional density, but you know what? I don't want to stress you through the calculus. I'm going to give you end result. Pay attention. Take a look at this. If y given s follow normal distribution, look at that. Y given s. Oh, maybe I'm talking about temperature. Maybe I'm talking about, let me see. Let me use a, okay, I want to go away from medical line. I want to go into banking. Maybe Y represent the proportion of time work in facility is used in a bank. And X represent the proportion of time driving facility. Of course, when you go to bank, you're going to see some customer, they're going to walk in, right? Some driving. Does that make sense? And they're going to be attended to, okay, through the window. If Y represent the proportion of time drive-in facility is used in a bank, and X represent proportion of time walk-in facility is used in a bank, and if the distribution of y given s follow normal distribution, as you can see, with a mu star, a sigma star squared, okay, based on the density that we have derived here, we can make a conclusion. Please pay attention. The conclusion we want to make is very crucial. Take a look at the conclusion here. That is the conditional mean. That represent conditional mean of y given x. Conditional mean of y given s, okay, it means expected value of y given x equal to something. Okay, if this guy represent proportion of time, okay, work in facility use, and this proportion of time drive in facility is used. Okay, now if I know the proportion of time the working facility is used, what can I say on average? What can I say on average about the proportion of time a driving facility is used? If I want to figure that out, I'm actually going to use this formula here. Mu y plus rho, okay, sigma y over sigma s, okay, x minus mu of x. And of course, since this is an average, then I need the variance too. And that variance is called conditional variance. The conditional variance is actually, which you can also, like this guy here, okay, is what I call mu star, okay, and this guy here is sigma square star. Okay, the sigma square star right now is actually sigma square y, 1 minus rho squared. I need you to pay attention. Please pay attention. When you are using a conditional function, there's going to be a conditional mean, there's going to be a conditional variance. But I need you to pay attention here. If rho equal to 0, can somebody tell me? If rho equal to 0 here and rho equal to 0, what are they going to become? If you take a look at that. If rho equal to 0, I'm only going to have this guy, which means conditional mean become unconditional mean. Or conditional mean is this guy. Do you see that? That's an unconditional mean. Unconditional variance is just this guy. The unconditional variance is just going to be sigma square y. The unconditional mean is just going to be that. So when the correlation between variable equal to 0, the conditional mean becomes unconditional mean. Another name for unconditional mean is marginal means. Another name for unconditional variance is marginal variances. Please pay attention. That is very, very crucial. Okay, now we have that how. Okay, we have that now. We can go into example. A statistics class takes 2 exams. X is exam 1, Y is exam 2, where the score follows a bivariate normal distribution with parameters. Now, you were given the mean of S and the mean of Y, which are the marginal means. And you were given the marginal standard deviations, and they also gave you the correlation. Okay. Now the question now is, suppose we select a student at random. What is the probability that the student score over 75 on exam 2? Then the student score over 75 on exam 2, given that. Now, I need you to pay attention to question A. Question A does not require the use of a conditional function because there's no conditional word. But when you take a look at question B, oh my God, pay attention to that. Given, can you see given? Then it means the function I'm going to use in question B is going to be conditional one. And of course, you see C, D, and E. Now, the C said the sum of each or exam 1 and exam 2 score is over 150. Then the student did better on exam 1 than exam 2. And E, the probability of 5x minus 4y greater than 150. Now, I'm actually going to show you how you can compute this manually and how you can make use of the R software. Wait a minute. Oh, I think 955 of 905 to 955. Okay. Now, look at the first one. The first one is focusing on Y. Okay? If you take a look at that. Y is exam 2. Can you see that? Exam 2 is Y. Can you see that? Okay. Because of that, we're only going to use the marginal distribution for Y because they're focusing on Y. I'm going to make use of the mean. I'm going to make use of the variance. Then I want to figure out the probability of Y greater than 75. You've done this before in the lower level statistics. You standardize, you check for that values in R, in table or R, you ask that as a probability. Now, how do you do the second one? Okay, the second one that is talking about conditional. Okay, conditional. Now, when you look at the second one that is talking about conditional, it said, if you come here, it said the student score over 75 on exam 2, given that the student score 80 on exam 1. That's a conditional one. Okay, in that one now, look at my interpretation. Please pay attention. You see my interpretation now? Now, because of that, I need a conditional mean formula and conditional variance formula. That's exactly what I've used here. Take a look at that. I've used the formula here. I just plug in all the parameter. Because I may not be able to find the probability here. I may not be able to find the probability here if I don't first find the conditional mean and conditional variance. And that is what I'm actually using here now. That's what I'm using there now. And finally, I got this result for that. The second one, for the sum, okay, you're talking about the sum of a random variable. The sum of a random variable will require the sum of the two means, then the sum of the variances, and 2 multiplied by covariances. That is the formula. When I plug that in, this is what I got. The variance, the mean, then I should be ready to find the probability using a z-score. I told you the other time, normality facilitates standardization, okay, which will make the probabilistic computation so easy. The same way I do s plus y, I can do s minus y. Look at that. Just use the necessary formula. Look at that. Okay. Okay, then I got that. Then I can also do 5y minus 4y, follow the distribution, using the formula once again. Okay, I'm going to get that. Then I'll be ready for that. But you know what? If you don't want to waste your time, that is the coding now for all for A to E, if you want to figure it out now. And what is next? Multivariate normal distribution on Friday. Is there any question for me before I go today? Any question? Okay. Okay. I think I don't have an announcement. Make sure you all stay safe and have a lovely day. Bye for now, everyone.